Okay, so we are 1 minute past the starting time. Let me kick it off. So welcome to session 3 on today, which is the 11th of May, Tuesday, and we will be covering chapters 6 to 7 today in the reading club, including the appendix. So just in terms of the agenda, quick refresher on the reading club. James Sharp will present chapter 6. I'm going to present the appendix and 7.1 and 7.2, and Fergal will present 7.3 to 7.7. So that's what we have on the agenda for the evening or the day, depending on where you find yourself in the world. And what is the reading club? Basically, we want to read through Nassim Taleb's new book, which is Statistical Consequences of Fat Tails, over the course of 2021 and perhaps stretching on beyond that. The book is available freely on the internet from archive. There's also a very beautiful hardcover edition that you can get. And hopefully by reading this together in a group, we'll have some discussion. We'll be able to learn from each other, and also there'll be enough scale to provide some code to reproduce and apply results. Just to acknowledge a couple of people, the network of consulting actuaries with which James is affiliated has provided us Zoom access, and we're very grateful to them for that. Fantastic organization, and recommend, if you have an interest in the insurance sector, that you go look at their website. Jake Billings for his excellent website that he put up for us at the link that you can see on the page, where there's also a link to recordings. And you can look on the GitHub repository for discussions and code. So thank you very much to everyone who has contributed to date. And with that, I'll hand over to James for chapter 6.
Okay, great. Thanks, Ron. Let me just share my screen. Or do you need to unshare your screen, Ron?
I will unshare, and a fantastic point has been made that we need to start recording, James.
Yeah, it should be going. I think it's recording. Yeah, it is. It is recording.
Great.
Yeah. Okay. Sure. So let me just share. So yeah, it's a similar approach to last time in that we have. I was going to talk through the paper itself, so the book, and anywhere where there's something a bit more perhaps to draw out, we kind of dive into some slides or some R code as well, which we've kind of got as well. So just make sure that I'm sharing the 3 pages. I think. Can you see the R code at the moment? Is that?
We can currently see the book.
Oh, the book. Okay, right. Let me just get the R codes. Okay, so should be these 3. Right, perfect. Okay. Right, yeah. So chapter 6 is it's similar to, the principles are similar to the previous chapter 4 and 5, except now we're kind of taking in this extra dimensions, so multi-dimensional problems. So it's similar concepts of fat-tailedness, but you have this really significant additional problem of further dimensions. And there's something called the curse of dimensionality, and I think that kind of plays through in some of the pieces in the next couple of chapters, as it really does make things a lot more complicated. The first page here, you can just see a couple of plots in the book which kind of nicely illustrate the difference between a normal distribution spread on this plot on the left and a kind of fat-tailed spread on the right. So on the fat-tailed spread on the right, you've got this very dense piece in the middle, and then much more broadly distributed points elsewhere compared to the normally distributed data on the left, where the information is kind of more spread out in a kind of more more normally distributed way. So the second page, this is basically talking about a multivariate Gaussian distribution. So there's a kind of formula for the Gaussian distribution, and so it looks very similar to the normal Gaussian, except this time it's multivariate. So this sigma, which in the univariate case would just be a single number, now this is a matrix, and these other numbers like this x and the mu, those are vectors now. So it's it's kind of similar principles to the univariate case, but now it's a multivariate case in many dimensions. And here we have in chapter 4, what is mentioned here is chapter 4.1. We at the last month's event, we had this sort of approach that that the book describes of how you would fatten a tail effectively. So you take a ratio between two different multivariate normal distributions, and you kind of simulate from one or the other. And we had some code on this on chapter 4 where we kind of looked at doing this, and it kind of fattened the kurtosis in the univariate case. Well, this is a very similar case. It's basically the same principle, but just expanding it to the multivariate case. So where we have this this matrix can be defined by matrix times 1 minus alpha, 1 minus a, or 1 plus a. So that's just the same mechanism effectively for fattening the tail of a distribution by taking this kind of formula, similar to what we looked at in chapter 4. Yeah, so there's some kind of nice pictures here of elliptical distribution. This is a student T, probably not too different perhaps from a normal distribution, but it looks very uniform. And here there's a non-elliptical distribution, looking much more ragged and not quite so nice. So it's got a stochastic correlation. We get on to what is meant by elliptical and non-elliptical in a bit later in this chapter. Then again, another nice plot. I think everyone can see probably why that's called an elliptical distribution, in the shape of a nice ellipse. And non-elliptical distribution is quite a different shape here, so you can see the difference there. So yeah, in this plot in 6.2, there's kind of visual illustration of a sort of fat-tailed movement around this space. So this gives, you can kind of simulate quite easily in that sort of shape. I probably should have done that in R, but you're kind of moving around this space with sort of big fat jumps, and each step is like a kind of quite a big jump, as you can see in this plot. And there's a nice comment here that this is how in the real world historical processes move, is in these kind of big jumps. We have kind of wars and pandemics, and during that period you get a kind of step change in the way things operate. So this is the way the book is arguing effectively in this sort of 80-20 Pareto style movements, compared to what it would argue is kind of the perhaps social scientist model, where things move in small Brownian motion style jumps or small tweaks. So that's kind of just a visual presentation of the two different descriptions of possibly how the world operates. So the next section is talking about elliptically contoured distributions. So it gives a definition for what an elliptical contoured distribution is. So it gives the characteristic function. That is it. It's a little complex as to what that means, but it is in principle, it is a probability distribution which has a kind of a covariance matrix, and it's kind of a range of distributions that fit into this world of elliptical distributions, which include the normal distribution as well as student T distribution. And the student T distribution also includes the Cauchy distribution. So it's a class of multivariate distributions that is widely used in finance. I put an example on the slides. This is something that is used in the insurance regulations, the European insurance regulation. We actually use this assumption, or the regulator does. So the European regulator, so it's kind of trillions of pounds worth of capital or reserves and so on are dependent on this formula working, and you can kind of find it in this link here, Article 164 of the EIOPA regulation, and they have this. This is the transition matrix, correlation matrix that they will use in the European regulation. So different risks, the interest rate, equity, property, credit spread, concentration, and currency risk. An insurance company would calculate capital requirements for each of these different risks, and then they would aggregate them using this correlation matrix. And the principle underlying that calculation is that the underlying multivariate distribution is a elliptical distribution. So this part is quite important because there really is a lot of practical implications from what's written here in the paper. So it's arguing that financial theory, these elliptical distributions have some kind of fundamental problems, and yeah, it matters because this is kind of what everybody's doing in lots of different regulations and so forth. They're assuming that elliptical distributions are okay to model these risks. So there's a point in this box here about diversification. So a lot of the diversification assumptions that you can get in what were these Markowitz style portfolio construction, where you have, I think Harry Markowitz came up with this model in the 1950s. It was based on assuming you could have a whole range of equities, and that by holding lots of them, you could get a certain level of diversification. So this is effectively arguing that the level of diversification you get is much lower, because this assumption that the distribution, multivariate distribution, is elliptical probably doesn't hold. And in reality, it has the assumptions fail, and that has some genuinely material consequences for your diversification. So you might find you think you're diversified, but in practice you don't get the same benefit as you're expecting. Section 6.3 talks about the multivariate student T distribution. So this student T distribution, it includes the Cauchy distribution for when the degrees of freedom parameter is 1. So it's quite popular in Professor Taleb's work, the student T, because if you have a degrees of freedom parameter of infinity, then that's the same as a normal distribution. If you have degrees of freedom parameter of 1, then that is the Cauchy distribution. So you get this range between like very thin-tailed distributions, the normal distribution, or very fat-tailed distributions, which is the Cauchy. Yeah, and yeah, some nice plots here for various different student T combinations. And here we have a kind of joint distribution function for the student T. So 6.3.1 talks about this issue of ellipticality and independence under thick tails. So it starts by kind of creating this joint distribution for two Cauchy distributions, which is captured here in this formula. And then there's a kind of in equation 6.9, we set this correlation assumption to 0, and we get this formula. So it's basically the same as 6.8, but the correlation is set to 0. And the key point about doing this is that whilst the correlation is 0, you don't have you don't get statistical independence. So this is a really important issue for some of the differences between the normal distribution and the student T and the Cauchy. That for a normal distribution, if you have this function and you set the correlation to 0, then it would become independent. But for the Cauchy or the student T, the paper here is saying that the correlation may be 0, but you're not getting independence. And then here's the formal definition for what you need to get independence. This f of xy over f of x times fy equals 1. So that's basically saying these are exactly the same and there's no interaction between the two different distributions. So for a bivariate Gaussian, if the coefficient is 0, then they are independent and uncorrelated. But as I was just saying earlier, this doesn't apply for the student T or the Cauchy. So yeah, that's an important feature really. Why? What are some of the key issues with when you get fatter tails, these student T and Cauchy distribution? You can get non-independence even if the correlation is 0. So yeah, this section here, 6.4, fat tails and mutual information. So this was something I had to look up. I have to be honest, I've not used mutual information before. So it comes from information theory side of statistics. So a number of sides of statistics, what tended to happen historically were that people in kind of different fields like agriculture or social sciences and so on would look at statistics from different perspectives. And one of the early ways in information theory, where people in the early days of sending things like information down a telegraph wire, people had to interpret whether they were getting a 1 or a 0. And there were a huge amount of statistics that went into this. And it was done somewhat independently of what kind of mainstream statisticians are doing in the kind of frequentist Bayesian fields. So they had this kind of new field called information theory. I've not really used it very much. I've tried to read up on about it, but this has really forced me to kind of get stuck into it and then try and understand what's going off. But in principle, it's another measure of correlation that's not the same as this this correlation parameter we discussed up here. So yeah, correlation parameter it's really kind of like a sort of standardized covariance parameter. But this formula for mutual information is slightly different, and it has some advantages. So I'll skip over this plot. I'll come back to that in a minute, because I think it relates to something a bit further down. But the yeah, so the mutual information, the definition of this mutual information is given by this formula, and so you basically need three things. If you have two different probability distributions, you need your joint distribution, you need your and your two univariate distributions, and then you can work out this parameter. And these values here are HUX, HY, HXY. They're what's called entropy, and that's a concept used in information theory. I'm not really an expert on it, but I have been reading about it over the last few days to try to understand this section. And what I found was that, yeah, can you guys see this in R? Is this coming through?
Perfect, James. Yeah.
Okay, great. Yeah. So just to kind of highlight the difference between like this linear correlation coefficient and the mutual information coefficient. What's the difference? We take a kind of a data set. So we've got X, which is like a sequence of numbers just from like -10 all the way up to 10. And we work out Y, which is just Y is equal to X squared. Then we work out, and Z is exactly equal to X. So, and then A, we set up another A is just, it's just 1, repeated 21 times. So, yeah, we can kind of plot these. The first one, we can plot X and Y. So X along the bottom, Y on the Y-axis. So you've got a nice X squared term. Then we can plot another line, which is X and Z. So this is just X equals Z on that red line. And finally, the third line is just A equals 1 all the way across. So I mean, in principle, you should be able to see that X and Z have exactly the same values. So these should be perfectly correlated, and they are. So you can kind of run that. So that correlation coefficient using R just comes up with 1, which is what you'd expect because they're exactly the same values. And X and Y are, we can work out this is the linear correlation coefficient, comes out with 0. So if you work out your linear correlation coefficient, you're plotting this black line, and we're basically saying that Y and X are uncorrelated, which is true. They are uncorrelated for this data, but they're clearly not independent because Y equals X squared. So when we're doing these elliptical distributions with these linear correlations, which are fundamental to those distributions, we have some loss of information, really. You're losing nonlinear interactions between different risks in this case. So is there another way of doing it? Well, to be honest, I've not really seen another way of doing it. I mean, I've seen like there are the way in finance I've seen that done before is you have like what's called a Pearson correlation coefficient, which is just this function in R, and then there's also a Spearman correlation coefficient, which is where you kind of just rank all the numbers, smallest to largest, and in that case that would I know it would still not work. I think, yeah, it would still come up with 0, but that in principle can identify, is more likely to identify nonlinear correlations than just the Pearson correlation. But in the book, it comes up with this new factor, so we can kind of see how that's working. I haven't tried to code it up myself. There is a library in R. Normally, if I was doing a piece of work, then I'd probably kind of code this up myself and then check it against the existing library. But in this case, I've been a bit lazy and just taken the standard R package and run it. So first of all, if we look at X and A, so X is our number, just -10 to +10. And if we type A, it's just ones all the way across. So in principle, these are uncorrelated. What we do to X has no impact on A. So if we run this mutual information factor, it comes up with 0. So that's kind of a good sign. It's basically saying there's no information. Anything you find out about X, it doesn't tell you anything about A, which is exactly what we'd expect. Then we can compare X and Z. So these are both the same. So we found we obviously got a linear correlation of 1. So X and Z, we run through this mutual information and we get 3.04522. I honestly don't know what the number is, probably some log value, but I don't know. So that is effectively our 100% correlation value in this example. Now, what we'd like to know is what's the link between X and Y when we're using mutual information. So it expects that there is some information in there that is coming through, because obviously if we know X, we can know Y. So what happens when we run this? Yeah, okay, so it's not 0. So it's a number in between 0 and 3. It's quite a lot closer to 3. So that's telling us there is loads of information in X that tells you about Y, which is it is a really attractive feature. So that is great. So yeah, that was quite an exciting thing to read through from my point of view. I've not used this before, but I could already think about using this for things like principal components analysis, where some of the relationships aren't linear, and you want to find non-linear relationships. You could kind of do that with using this this kind of correlation instead. So I can already see loads of applications. I have to say I don't know if there are any limitations, but yeah, there's a lot of opportunities for looking through that in more detail and perhaps trying to apply it to finance and possibly the regulations as well. Might look at doing something along those lines as well. So this kind of thing where we've got this elliptical assumption, it could be reviewed, and possibly a different approach might change the way the European regulator looks at this. But yeah, anyway, pressing on to the next section. So this piece is section 6.5, fat tails, random matrices, a rapid interlude. So this really is it's an interlude, but there's just so much information. This is like just a few paragraphs, and for me, again, this was quite a lot of learning I went through here to get this. But this is basically looking at, in this case, it's kind of, I think we've brought this in here as an interlude because we want to know what is the impact of fat tail distributions on matrices and some of the key features of matrices. So we have a really nice kind of example of this, and this links back to these plots up here, and I'll kind of talk you through these. But before doing that, the reason I say there's a lot of information in this section is it assumes knowledge of eigenvalues and eigenvectors, and it assumes knowledge of random matrices. So, I mean, most people who've done a maths degree or something would be familiar with eigenvalues. Random matrices are not so common, so I had to look that up. And there is a book on that, a really wonderful book actually I found, which is free. So this book here, you can find out about what a random matrix is, and kind of simulate from them, as we'll talk through in a second in R. I also put this kind of brief summary on eigenvectors and eigenvalues. It gives a kind of just a description for what they are. The book kind of assumes knowledge of them, but anybody who's a bit rusty on the stats from university days, here's just kind of a brief overview of eigenvalues and eigenvectors. It's kind of a simple kind of identity which defines an eigenvalue and an eigenvector. If you have a matrix, you have an eigenvalue and your eigenvector. Sorry, eigenvalue is this lambda, eigenvector is v. So if your matrix has 2 dimensions, you'll have 2 eigenvalues, 2 eigenvectors. If your matrix has n dimensions, you'll have n eigenvalues, n eigenvectors, and you find the values and vectors by solving this equation. And in practice, you usually need to use some kind of numerical algorithm to do that. There's some stuff on the internet for doing that in VBA. In R, it's really easy. There's a 1-line code eigen, which is kind of really amazing that R just solves it in 1 line, because that's a really complex numerical problem. But yeah, in R, it's built in. So I tried to have a look at this piece in R. So what's happening here? So it talks about eigenvectors and eigenvalues here. It gives that kind of that equation where you kind of solve to find out the eigenvalues and eigenvectors, and then it describes this equation, which is the equation for the eigenvalues for a random matrix of size n, and it kind of plots these here. So for a Gaussian random matrix, I'll describe what that means in a second, but you get a shape like this for your eigenvectors. For a stochastic volatility random matrix, you get a shape like this. So it's kind of fat-tailed. You can see the tails are further out, and there's a bunching in the middle. For student t with 3/2 parameter, you get a huge spike and then massive tails. For student t with 1, remember that's the Cauchy distribution, you've got this just basically a spike. So I had a look at that in R. So there's some code here, and yeah, there's a little function here for a random matrix. I'll just briefly explain what that does. But it creates a matrix of kind of size n, so it's n by n matrix square, and each value is from a random normal distribution with mean 0, standard deviation 1. So we could kind of parameterize these, but for this example, I haven't. Yeah, so it just creates a matrix where every single value in the matrix is a random number from a standard normal distribution. So that's what we mean by random matrix. I didn't know that, but it's explained in this book here. That's what we mean by random matrix. Yeah, but there's a problem with that. If you just do that and you try and solve for the eigenvectors and eigenvalues, you'll find that the eigenvalues are complex, so they become complex numbers. So you can't solve the equation without using complex numbers. So you can, what you can do is take the matrix plus its transpose divided by 2, and that gives you the a kind of symmetric matrix. So if we just we can just kind of type in, we just type that rand matrix. Ooh. I'll just give an example so you can kind of see what's going off. Yeah, so if it's just like 3, so yeah, so it just creates so it's symmetric. So this number here is equal to that number here. This one here is equal to that number here. So it's symmetric about this here. So the bottom left is equal to the top right. So it's symmetric. So if you have a random matrix of this type, you can find eigenvalues which are real, not complex. So that's what we've used as a random matrix for this example. So I've done one for a normal distribution using this code, and then there's a second function for a random matrix for a student t distribution. So it's yeah, it's very easy to do this in R. So this is quite a complex calculation again, but you can just use this random number generator that's embedded in R. So for a student t distribution with degrees of freedom df, and we can create a matrix. And then in the next piece of the code, we can kind of we can work out the eigenvalues. So I've got here this random matrix of 1,000 by 1,000. So we can kind of plot these 3. So we can work out there must be so there are 1,000 eigenvalues for this matrix. So we've created this massive matrix there, which might take a few seconds, and the student T one as well. So that's the student T with 2 degrees of freedom, not quite the same as the I think this was 3/2 in the book. So this, I think this is what the book was doing, and I don't know if it didn't actually describe the exact formula they had for a random matrix, because there are a few different possibilities, but yeah, then I kind of plotted this in histograms. This is the normal distribution. Maybe it's not too far off. It kind of looks a bit like a semicircle there. So that's your normal distribution, your distribution of eigenvectors. For a student T, slightly fatter tailed, you've got that big spike, which you see in the book. And for the Cauchy, yeah, it's just like basically everything in this central point, and then these kind of wild tails, massive numbers either side. So just enormous eigenvalues. So that's basically almost all of the data is being governed by just some of the points. That's what it's saying. So that's what Nassim was saying, I think, when he was talking. That was his definition of a fat-tailed distribution, where almost all of the movement is governed by just a few data points. And that's the same thing we're seeing here. So that's our kind of interlude there on these random matrices and the eigenvalues, and the distribution of those eigenvalues is kind of covered in 6.5. Yeah, so section 6.6, correlation and undefined variance. So this is a really important point as well here, is what happens when you you have these parameters with undefined variance, and what does that mean for your correlation parameter? So some kind of equations here which should take you through how this is kind of derived, but basically the principle is that the variance is, it could be infinite, or the covariance can be infinite, but the correlation itself is finite. So it has a number. So your correlation coefficient is always between 1 and -1, and so it will have a number. Even if your covariance is infinite, you've always got a correlation. But the book here is saying that even though it exists, it's not usable in practice. So it's you have a value for correlation, but you shouldn't really be using it if your variance and covariance are infinite, because of some of the reasons. I think in the next chapter you've got these kind of law of medium numbers and so forth. There's a nice plot here for, I think, IQ. I think this is IQ, and I'm not sure what the other so income. Yeah, there we go. Yeah, so IQ and income. So I've seen some debates on this on Twitter with various social scientists and so on, but it seems to fit very well for a large part of it, but outside a certain range, it just has no link whatsoever. So I think that's this is probably the key point that Nassim was alluding to in some of these discussions, and yeah, and linear regression. So there's a nice piece here on linear regression. You've got this kind of characteristic formula for linear regression. The way most statistics courses talk about it is this parameter here has a normal distribution. So there's a whole load of theory around linear regression and how to fit with your kind of normally distributed parameter here at the end. But in this example, we have, I think we're looking at Cauchy distributed errors. So yeah, so in this example, we've got Cauchy distributed error, so power law distributed. That's the key difference with this example. And this possibly the case, many of these social science experiments, where you have people fitting linear models to things, but the errors, on the basis that the errors are normally distributed, but in practice they kind of power law distributed. And the consequence of that is you've got your R-squared parameter, which is used for kind of justifying how good the fit is. And you've got this equation, when you kind of plug it in, you get this number here. And the expectation of a Cauchy is kind of tending to infinity. So the expectation your R squared is 0. So that's just a theory. If you have these kind of power law, this epsilon, then your R squared is theoretically 0. Even if in practice your sample, you've got a value that's not 0, your kind of theoretical, it's just kind of luck or bad luck, perhaps is the right word. Yeah, so there's a nice discussion here. I did a bit of stuff in R here as well, just to kind of visually present this. This sort of formula here. You've got a kind of X is just a sequence. You can kind of read in A and B, and your error term is a Cauchy. So just to simulate from that 50 numbers, and then just plot and see what happens. Yeah, so you can kind of see there, it looks correlated, but you've got these big spikes coming out. So like this one, so it's kind of 1 point right out there, which is hidden behind. Oh yeah, so that point, so these are all kind of on the line, and then you've got some other point that's just miles out, because the error terms are Cauchy, and every so often you just get these enormous spikes. Yeah. Okay. So yeah, so that was the key point of this section. When a fat-tailed random variable is regressed against a thin-tailed one, the coefficient of determination R squared will be biased higher and requires a much larger sample size to converge, if it ever does. And he kind of draws on this example of IQ, wealth, IQ, and income as particularly prominent examples of that case. Okay, so I think that's the end of chapter 6. I think it's I can hand over to Ron for the next section on chapter 6 appendix.
Okay, James, thanks. That was fantastic. Maybe just before we hand over, let's see if there's any questions from the audience or any comments. I also see that we are joined by Nassim himself, so perhaps James, we can make him a co-host and hear some of his input. So we're very privileged and delighted to see Nassim here as well in our group.
Let me do that. There we go. Okay. Okay.
Sorry, yeah, very honored, but let's assume I'm not here. I'm just an observer. Take notes, as you can see. Okay.
Perfect.
It's impressive. I've learned more from listening to you than I have from doing this stuff.
Yeah, that was very impressive, James, and I don't think you get much higher praise than that.
I just have maybe one comment I'll make at the end with different information.
Now is good too, while it's in everyone's minds, Nassim, if you'd like to make it.
The main problem is that mutual information is what you know is entropy. We have a problem with continuous versus discrete entropy. And mutual information is really designed for continuous distribution, not for discrete distribution, or unless you have a huge number of points. So what happens is, what you did was correct, but you're going to realize that you get two different numbers if you do the following. If you take the points, okay, and then derive a histogram, what we call empirical distribution f of x and y, or if you actually do what we call a kernel, you create a pseudo-continuous distribution out of it. You get a different point. If you want, I can draw, but you know,
Sorry, yeah.
Sorry?
Yes, please. Yeah, that would be great.
All right. So I have, let me get my chalk. Let me raise this. I've got my chalk. This is here, okay. Just that when I do mutual information, I'm looking at f of xy over f of x, the products, okay? Log. So, given the problem is, if you compute, you need to again exact this f of xy, the way people do it, if you do an empirical distribution, then you have a something like a histogram, you see? Okay, so one way to solve it is to have a smooth histogram. And that's a kernel distribution. And use a continuous distribution inside a function. Because otherwise, in discrete time, what you're doing is you're summing, you see? You do a sum of x, y, xi, yi. You do the double sum. And you get a usually different numbers between these two. So the way I try to get mutual information is by smoothing. And there is a mathematical function that smoothes the distribution.
Yeah.
So in other words, instead of having samples, you get, instead of having samples and then working with, summation, you see, you're because this is going to be, this is xy is going to be, and then I have sum of x, sum of f of xi. As you can, sorry, not sum. The sum is outside the log. You see, the sum is outside the log. Okay, and then at some point, sometimes the thing blows up. Often blows up. Or do it discretely. Never when you do it continuously. Is this clear, or should
I think so? Yeah, yeah. I did see in the R standard code there were 3 different methods that they use for discrete. And I think one of them was probably, the one used there was probably some kind of smoothing, like you described.
Yeah, you smooth it, so you have a function. And once you have a function, then that log always holds, because what you're doing is you're summing logs, okay? You're summing, okay, now, sorry, I made a mistake by saying you're summing the logs, okay? All right, you're summing the logs. So at some point, you may have a 0 frequency. Because of sampling discreteness, the thing blows up. Okay. You see? It's going to be minus infinity, you see? And then whatever you sum up with minus infinity is going to be 0.
Okay.
It's going to be minus infinity, so it's not going to count. So, sorry, I was not concentrating on the point, but so there are 3, effectively there are many methods. Okay, the method I use is what I call smooth kernel. And it doesn't matter how good your kernel is, so long as it's smooth, that you have a function. And then you integrate instead of summing.
Okay.
You see?
Yep. Yeah, that's helpful. Yeah. Okay.
Now, one importance of mutual information, regardless of the method you use, is the relative distance between points. Okay. This is correlation. Okay. 0, say 1/4, 1/2. Okay. When you look at mutual information off of these, it's going to give you the same ordinal, ranking. But guess what? It's going to give a lot bigger number for larger correlation. So because mutual information, that's rho, that's mutual information is going to be like this. Convex. Actually, it reaches infinity for the rho of 1. And also on the minus 1, also like this.
Okay. So range is minus infinity to plus infinity.
Yes. So what happened, but it stretches the map. So 1/4 is a lot closer to 0 than 1/2. So if you were to do it again, okay, the corresponding mutual information is the same for this one and this one. This one will move to the left, because look at this function.
Yeah.
And if you ever do entropy, general entropy, like Kelly criterion, which is based on entropy, you realize it's an exact fit. How much would I bet on Y knowing X? You see, the strength of the signal you're getting is a direct bet. But anyway, within this context of fat tails, I was showing how fat-tailed distributions map to mutual information. So for the Gaussian, rho equals minus, I think, log of y minus rho squared. Okay, that's a Gaussian. As you're seeing in that chapter 6, if I have a fat-tailed distribution, it's no longer that simple. So for a Gaussian, if I want to translate directly from this to an entropy metric, which gives you a better sense of what's going on, okay, the equation is direct. You see, I take correlation, I say, what is it, 0.05? It's zero mutual information, you see, or close to zero. Quarter, close to zero. Half, we're talking, you see, correlation of half. So with this, using this mapping, for the others, more complicated. And we have nonlinearities, of course, then it's nonlinear, then it doesn't work at all. Okay, so sorry to barge in with this.
That's very helpful. Thank you.
Thanks.
Great. So I see that Marcos has kindly put a link to a paper of estimating mutual information using kernel density estimators, which looks very interesting. And then I provided a link which purports to show the link between a copular function or a particular function of a copula that they call copular entropy and mutual information. For those people who do a lot of copular modeling, that might be very interesting. So this has definitely been quite inspiring in terms of finding out about new things, and now I've got to figure out how we actually go ahead and apply it. So I'm going to carry on, if that's okay with everyone, with the appendix, which is between 6 and 7, and then I'll talk about 7.1 and 7.2. So this appendix is something very interesting to me, because what I found in a lot of cases, we think about distributions as these idealized bell shapes, but in a lot of situations that are common in financial practice, you actually have a binary event, which is what you care about. And where this is popped up, at least in my world, is when you think about credit risk. If there's a default, this is a massive problem. Most of the time there isn't. And then that's until it is. And then you're in what we call a violent regime in this particular chapter, and things fall apart. And in this case, you don't have these very nice idealized distributions. You have almost these binary events. And this is really what this chapter is about in my mind. It's about these multimodal distributions where you don't have a single curve, but you have got a combination of two events, often one of them being quite rare. And to kick it off, we've got this figure, which is the coffee cup problem. Most of the time, your coffee cup doesn't incur any loss, but if it falls on the floor, it's very likely that it's actually going to shatter. So in terms of the distribution around the damage, maximum damage is where you've got the majority of your probability density. And then these smaller damage amounts to the coffee cup, that's where you actually have very low probability. And this is almost a theme that we'll see played out throughout this chapter. So what we saw in the previous chapter in 4.1, we have this example of what happens when you have a Gaussian distribution where the variance parameter switches with some probability. And what we saw over there is that this switching in probability leads to fatter tails. And what we're going to do in this chapter is stochastize the mean, which is add the switching behavior to the mean of two Gaussians as well, and see what we get in terms of these multimodal graphs or multimodal probability distributions, but also what we get in terms of the impact on kurtosis. So over here, we have a very nice example. We'll go through these in a little bit more detail. But this is really one of the key statements in this appendix for me, which is that the meaning of thick tails, the way we understand what kurtosis measures, is actually different in the multimodal situation, or unlike kurtosis, where you've got this kind of, unlike normal unimodal fat tail distributions, where you have this bunching towards the center and these fat tails, you actually have the opposite, where the expectation around the middle of the distribution ceases to matter. And that's where you have the lowest probability distribution. So that's the lowest probability density. And that's what we'll be looking at in this chapter as we go through. So in this paragraph, we give a couple of real life examples of where you have this type of regime switching or bimodal behavior. And the paradigm that we're going to follow over here is that you've got two different regimes, a calm one and then a violent one, and each of them has got their own expected mean parameter and standard deviation parameter. And as I was saying earlier, at the extreme, many of the events in finance and insurance are exactly this type of bimodal distribution, where most of the time your bank doesn't default, most of the time your reinsurer doesn't default, and most of the time a catastrophe doesn't occur, but there is this slim chance that you have an outcome in the other mode, and that's when a lot of trouble happens. So in the case of a Gaussian with switching means and variance, what is shown over here is that the kurtosis is a function both of the mean and the variance. And this is something I've never seen presented before, but you can see that it's 3 minus this function, and this function depends on the difference between the means squared. Doing a little bit of maths, what is shown is that to maintain the same kurtosis as a Gaussian, in other words, to keep it at 3, you need to have your variance in such a way that the difference between the mean is constrained really by the variance. And just given almost how fragile this metric is, I think in almost every case where you have a bimodal distribution with different means, almost guaranteed that you're not going to have a kurtosis sitting at 3. So what we have over here is the moment generating function, sorry, the characteristic function. And maybe just as a word of introduction, there's a lot of mention of characteristic functions in what follows. Characteristic functions are something, at least in my education, I dealt with quite briefly. They've got this very nice property that if you differentiate them, the moments of your probability distribution drop out. And that's something that's exploited quite heavily in this appendix and also in the following chapter. So they look a little bit intimidating. There's quite a nice introduction on Wikipedia. And just remember that this is really a different way of characterizing the probability density of a probability of a distribution, and that if you differentiate it, you get out the means. And over here, what we're saying is we are summing up the characteristic functions for n Gaussians, and for n equals 2, what's provided in this appendix is the formula for the first up to 4th moments. And you can see these formulae over here, and you can also see how your 4th moment, which is related to your kurtosis, actually depends on the first moment and the second moment. And again, that's quite unintuitive. And this is something that happens in these bimodal distributions, at least it was unintuitive for me. So there's 2 different types of bimodal distributions which we consider. One is a war and peace model. So you have a calm period with a positive mean and low volatility. And then you have a different mode, which is turmoil with a very negative mean and low volatility. And this is represented over here. What you can see that the kurtosis is 1.7, which is almost half that as a Gaussian. The other one that's considered is a bond. So if you invest 100 Rand, sorry, I should say for an international audience, $100 in a bond, and you're earning, what do you earn in developed countries? 2% if you're lucky. At the end of the period, you might get your money back, $102. And that's generally quite likely, but there's also the possibility you get nothing back. And you've lost your 100 Rand investment. So $100 investment, you'll have to forgive my South Africanisms. And this gives you this type of payoff where you have some probability mass over here, and you've got another mode. And I understood that this was representing the mayhem or the violent one where you've had a default and you're really unsure of what the value is going to be. So this is actually quite common in finance. Let's have a look at a couple of examples. So just for a little bit of revision, this is going back to chapter 4, which we covered last session. We've got a Gaussian distributed with a mean of 0 and a variance of 1, another Gaussian with the same thing, except it has a variance of 2. And we have a mixing parameter. I think I have a mixing parameter of 50%. And you can see that the mixed distribution that I'm calling stochastic variance, it's got this much fatter tail that goes out. And if we measure the kurtosis, at least the sample kurtosis, for each of the Gaussians imperceptible from 3, as we'd expect, the stochastic distribution has got 4. So that is revision, nothing new here. The case that we're talking about in this appendix is where you have both stochastic mean parameters and stochastic sigma parameters. So again, we've got our two Gaussians, except one has a mean of -10 now, and the other has a mean of +10. We've maintained the variance at 1 and 2 respectively. And you can see we get something very similar to the War and Peace model, a kurtosis of 1.77. So I guess what this means, going back to the what was said in the beginning of this appendix, in the middle, you've got very low probability density. So, and you almost never expect to land up around 0, even though that's where the actual mean of the distribution is. So just going back to what we stated over here in the beginning, that expectation ceases to matter. And this is almost the opposite of your normal fat tails, where you have a lot more clustering. Here with a bimodal distribution, you have no density around the expectation, or we have to think of a different manner of referring to thick tails, in this case of a bimodal distribution. Here is an interesting case where I've tried to do your bond payoff. If you get it right, you'll earn $102 at the end of the period. If you get it wrong, you lose your capital outlay, so minus 100. I've just, one of these has got a little bit of a wider distribution. You can see if I zoom in, the other is very concentrated around 100. In this case, interestingly enough, our kurtosis actually goes up. And this is probably related to the combination of the mean and variance parameters. So what this really means in one way of interpreting it is, if you fear there may be a bimodal distribution, especially if you're normally stuck in one regime, be very careful about your interpretation of the sample kurtosis, because you may have one number coming out, but if there is in fact regime switching and you can jump to a different mode, you can get a very different number, and that can have substantially different implications. And I guess what this really means is you'll never see the mean. So a lot of what we're comfortable with from statistics stops applying. This is the appendix, then gives a couple of other examples of these bimodal binary types of outcomes. And then what we move on to is something very interesting, which is this is a one-period model. What happens in an n-period model, where you in fact can transfer between different regimes? So this is a transition matrix that I'm highlighting with my mouse. Is very similar to what you find in a Markov chain. Your probability of being in state 1, if you started in state 1, is in the top left of the matrix. Similarly, at the bottom right of the matrix is your probability of being in state 2. You started in state 2, and on the off the main diagonal, you have your probabilities of actually making a transition. And then after n periods, so in other words, you run this for n steps, your probabilities of having switched are now represented by Bn and Cn, and your probability of staying in the state are represented by An and Dn, and these are given explicitly over here. What's very interesting that we continue to talk about is, let's say you have an absorbing state. So in other words, if you have one of these probabilities where if you get into the state, there's no way of getting out of it, then you're guaranteed in the long run to fall into that state. And that's given very nicely by the equations at the end of this appendix. You can also see what the eigenvalues and eigenvectors of this transition matrix will be. So just a very simple example. Here is a credit risk example. Most of the time, you're getting your money repaid to you, and that's going to happen with a 99% probability. The 1% probability, which you tend to ignore if you're investing in bond portfolios, unless you really are very risk averse, is you're not going to get your money back. There's going to be a default. And once you're in default, you are stuck in that state. There's no way of getting out. And then just very simply, I'm showing these 4 probabilities of the matrix as we run our end period model for 1 period, 5 periods, 10, and then 100. And you can see that this green column, which represents the probability of landing up in the default state, given that you started not in the default state, you can just see how that gets bigger. So if you keep doing this and playing this game, eventually you're guaranteed to run into a default. This is obviously with some simplifying assumptions that your probabilities remain stable, but it does give you some pause for thought that if you are exposed to the probability of a catastrophic violent mode, which is what we've been talking about over here in the War and Peace model, be prepared, because one day you are going to land up there, and that's what the downside will be. So that's my reading of the chapter. Oh, sorry, of the appendix. Just before we move on to chapter 7, and I'll be taking you through 7.1 and 7.2. Let's pause and just see if there's any discussion from the audience. I see Marcos has given us a regime switching example. Let's see if we save that, what happens. Maybe I can open that up. And he says this is pre and devaluation regime. So when you have a currency devaluation, you have this nice period of stability before you have that occur, and then basically everything falls apart and you flip into a new regime. And that's very similar also to, I guess, what happened with the Swiss franc when their currency peg against the euro broke. So this is the example shared by Marcos. You can see USD versus, that must be the Brazilian real. You can see we had this very nice period of stability where there was some sort of peg against the dollar. And often what you see when you look at pegged currencies, very good stability, but what's being disguised over here is the fact that you can have a switch into a different regime, and that happened in about 2000, and boom, suddenly you're back to insane, crazy volatility, especially in the beginning. So I guess the message that I took away from that chapter is if you seem to be in a stable regime, what you always should contemplate is, well, what's the exit point where you might land up getting out? And is there a transition probability out? So let me pause there and see if anyone would like to say anything else. Okay, let's carry on with chapter 7. I think I got the easy part of chapter 7, so I'm quite excited that I can hand over to Fergal to do the harder bits. And what we're going to be discussing in this chapter, this is really about the very beautiful statistical theory that often doesn't hold in practice because we never get to the asymptote. So we're going to be talking about the laws of large numbers and the central limit theorem. And this is a very beautifully put in the beginning of chapter 7. What's the limiting behavior if you sum over or average many random variables as you approach infinity? And I guess where we're going for the rest of the book is, well, before you hit infinity, depending on the statistical regime that you're in, what actually happens. So we talk about two types of, two of the different laws of large numbers, the weak one and the strong one. What we're doing over here, we have our normal assumptions of an infinite sequence of draws from the same probability distribution. So these are independent and identically distributed random variables. They have a fixed expected value, obviously. And what we're going to see is that as you average over more and more of these, your sample mean tends to your true mean. And this is the statement of the law of large numbers. What we'll see in the central limit theorem is that you can actually put a distribution on the sample mean, and you'll see that it's distributed with a mean of the true mean and a variance that decreases with the square root of the number of observations that you've got. What we discuss then in the book is that there's two modes of understanding convergence. You can have convergence in probability. So in other words, once you've converged, you can make a probability statement. And then you have almost sure convergence, which is similar to pointwise convergence. In other words, you can make an actual statement about where you're landing up. So let's have a look at the statement of the weak law of large numbers. Basically, what it says is that if you take the mean of very many draws from this independent and identically distributed random variable, as the number that you are averaging over tends to infinity, you will converge in probability that your sample mean will tend towards the true mean or the true expected value of the distribution. The correct statement is that the limit as your number of summands tends to infinity, the probability that you are more than epsilon away from the true mean tends towards 0. And the proof for this is based usually on Chebyshev's inequality. This is a very nice and interesting Chebyshev inequality that's worth understanding a bit more detail, that relates the distance between a random variable and the mean from the distribution from which it's being drawn to its distance in the number of standard deviations. The strong law of large number doesn't give you this limit in probability. It actually tells you that the probability that you have converged to the mean is unity. In other words, that's definitely going to happen. So these are two laws of large numbers. There are some interesting counterexamples that I saw on Wikipedia where the weak law may hold, but the strong law doesn't hold. And if you like these sort of counterexamples, that might be something quite interesting. I found this section extremely interesting because this is, what can you do to relax some of the RD assumptions? In other words, that you're only drawing random variables from the same probability distribution, and they're all independent. So Kolmogorov showed that you can draw from non-identical distributions. But if you're going to do that, then these distributions all need to have a finite second moment. In other words, they must have a variance parameter which exists. You also can get away with some independence. And that independence basically says that in your series of random variable draws, the further that these are away from each other, in the limit at infinity, the covariance between those has to be 0. So in other words, you've almost got like this 2D spatial dependence that you find in spatial random effects models or something similar. The closer together the random variables are, the more correlation they can have. But in order to have the convergence of the law of large numbers, variables that are very far away from each other in terms of when they were drawn have to have 0 covariance. Then there's two papers over here which are quoted, I believe, at least Kozlov is in Russian. I'm not sure about Bernstein, but you can weaken some of these conditions that the sum of the variance needs to only increase at n squared. And then interestingly, another type of decay condition on the covariance, so that as your covariance needs to be less than and equal to this particular function, which has this property that as you sum this function up over larger and larger distances between the samples, what you get is that this sum tends towards 0. And in some way or another, the way you can understand that is the further apart observations are, the less correlation or covariance that they have. Let's have a quick look at just some very simple examples. Here's just the law of large numbers. It's good to see that it works. This was done in R. On the left, we have 1,000 random draws from a Gaussian, and we've taken the mean 1,000 times. You can see we're converging pretty close. And then if you increase that by a factor of 10 to 10,000, the mean of 10,000 random draws from a Gaussian, you can just see, if you look at the x-axis, that the scale is much reduced. In other words, we've compressed this down a lot. You've got a much less varying distribution, as you would expect. Then we go on to discuss stable distributions. And I think stable distributions are, the way to understand it is these are when you have draws from these distributions and you add them up, and that's represented as Sn, the sum stays or tends in distribution to the same distribution from which you were drawing the random variable. So let's just run through a very quick example. Let's say you're looking at a Gaussian and you have 10,000 draws from a Gaussian and you sum them all up. because the Gaussian is a stable distribution, the sum of all of these variables minus an divided by bn will converge in distribution to another Gaussian. So in other words, the sum, absence the sum coefficients which you need to subtract out and divide by, keep the distribution. So this is distributions that are stable under summation. This is explained very nicely over here. You sum up random variables with any members of the class that of stable distributions, and you stay within the same distribution. Here's just a very simple example. What we have over here is 1,000 sums of 1,000 draws from a Gaussian. So in other words, we did 1,000,000 random draws from a Gaussian. We took the sum, and we just were very simply plotting that over here on the screen. And you can see you have something which has converged in distribution, or looks very similar to a Gaussian. And that's showing that the sum is distributed in the same way as the underlying random variables. What we have as well is the characteristic function. This is quite complicated. There is some nice explanation intuitively of this, again, online on Wikipedia if you're interested. I was wondering a little bit, and maybe this is a question for the audience and people who know more about this than me, what about distributions that are stable under a product? So in other words, if you have a one random variable and then another, you take another draw from the same distribution and you multiply them together, you stay in the same distribution, and that's quite a well-known property of the log normal distribution. So I'm quite interested to know if there's such a thing as a distribution that's stable under a product. Intuitively, the log normal should be, because it's really just the exponential of a Gaussian. I was quite interested to see if anyone knows if there is that characterization of these distributions somewhere else in the literature. So the well-known distributions in this class are the Gaussian, the Cauchy, and the Levy distribution, and these are defined by this alpha parameter in the characteristic function. Okay, now what we discuss is the law of large numbers for the stable distribution, and there's this very nice result that as you have an infinite number, as you tend towards an infinite number of draws from these stable distributions, you tend to the Dirac delta function at the mean, and this is shown in figure 7.3, which just shows you to that as you are having more and more draws of characteristics, the PDF, the probability density function, is stabilizing with a very tall peak at 0. And that basically shows just the law of large numbers for stable distributions in action, that as you accumulate more in your sum, you land up with the mean. And that's what's illustrated here. So I'm going to stop there. Let's see if there's any questions from the audience, and then I'll hand over to Fergal. Come, there must be some questions. Okay, no questions. So I'll hand over to Fergal.
Yep. Ron, sorry, I just have one question now on the transition matrix. What was the key takeaway from that transition matrix section?
I think there's two key takeaway, James, for me. We can ask Nassim as well, but my and probably a much more sound answer than what I'll give. Probably the one is that if you're in a very stable regime and you're thinking a lot about one part of it, always just think about if you can jump to another part. Particularly if in an end period model, there's an absorbing state. So if that jump is something to a state where you really don't want to be, and that's catastrophic, that's really problematic. And you can be fooled into thinking that doesn't exist if there's a very low probability. Those were my takeaways. Maybe we can refer to Nassim.
The same. I mean, he gave you the answer. You gave us the answer, Ron. The thing I would add is to generalize from this to something even more interesting, which is practically that everything is a Markov chain. And if you have you're trading P&L as an absorbing barrier, you don't come out of it. But so to summarize the idea of that ergodicity, because this is ergodicity, you see, if you have ergodic states, in other words, you end up having two end-up probabilities. It means no matter where you start, you'll end up there. then it's an ergodic Markov chain, you see, and then it means that there is such a thing as a long run. Otherwise, you're going to get stuck in one state and you will not arrive at the end. If one of the, say you transit from 1 to 2, 2 to 1, and then stay 1 to 1 or stay with 2 to 2, so long as no probability is 0 and no probability is 1. You see, so in other words, if you hit state 2 and the probability of staying in state 2 conditional on being in state 2 is 1, you get stuck. And you can see it easily the way you do it by multiplying matrices. So you multiply it over time and you see how the long-term probabilities, you're going to end up with probability 1 in that state in which you are absorbed. And there are even repelling states, you never stay there. You have 0 probability of staying and 1 probability 1 of transiting. So, but the interesting thing Ron discussed is that he said you have catastrophic risk. You never come out of it. Or you can have, as we do in finance when we model default, the company may come out of it. There is a probability of exiting, that war state or that bad state. But the most interesting thing is what Ron mentioned, is that when I look at a bond trading today at 100, you know that the future value of 100 is the lowest probability. You're more likely to get as outcome 102, because you got to add your coupons, or 50. You see the idea that the forward rate is that it has the smallest probability mass.
Yeah, and in a way, what's strange about it is in your normal case of fat tails, you have all of your mass concentrated in the middle. Here you got nothing.
Exactly,
it's the opposite.
Bingo. Exactly, this is bingo. So for example, when in the case of fat tails, you buy it at the money straddle. Okay, you're wasting your money because odds are, okay, you're going to lose, that premium. The mess is all here, and there's a small probability going away, and the straddle doesn't help you much. You see, it's too linear, so it's not worth the risk. In this case, you buy straddle. Okay, you buy an at the money straddle. You have the smallest probability of losing your. In other words, your worst case scenario has the smallest probability, which is losing all your premium. So yeah, Ron got it right. Your mess is not in the middle; it's away from the middle. These are weird cases that Brazilians know, as Marcos has been given us plenty of papers and examples and case studies here, as we're talking, because he's a Brazilian, so they know. Russians and Brazilians know about these things, because in emerging markets you have quiet currencies, and then explosion, and then quiet currencies again, and the forward. When you buy an at the money forward option, it's not going to be worth 0, because either you get your return on your way, okay, or it's going to blow up. And so one final example is mergers. Company A trades at 100. Company B decides, okay, I'm going to buy company A for 150. The market goes to 100. So either company B is going to be approved and finalizes the merger, will go to 150, you get 150, or the merger fails, goes back to 50. So 50 is the lowest probability that you have. Again,
it feels like a lot of our tools break down in these multimodal situations. A lot of the kind of basic statistics that you have and intuitions you have just fall away once you have a bimodal distribution.
100%, and particularly where the things that are most affected are option pricing.
Yeah.
People don't realize that an at the money straddle should be worth a lot more than out of the money. Out of the money is worth much less than at the money relative to the Black-Scholes or to Gaussian distribution.
Got it.
It's the exact opposite. It's the exact opposite of fat tails. On the fat tails, you pay for out of money option and you sell the at the money. Here, you buy the at the money because that's where you have the smallest premium risk and the biggest bang.
So for those of us in emerging markets, I think we have a new option strategy to try out later tonight. But let's hand it over to Fergal to take us from 7.3.
All right, thanks, Ron. Let's get a screen share going. Finding it on Zoom. Can you see me okay? Screen?
Yep, we can see your desktop.
Great. Right. We're going to start with the uniform distribution here. So this first part overlaps with Nassim did recently on his YouTube tutorial on this, which you should go and check out. It's following from what Ron was saying, and before I show a code example, there's just the worked out expression here shows you the distribution if instead of sampling just 1 point from a uniform distribution, you're sampling n points. So you do n times from a uniform, and that's your sample. And then it will look like this instead of just a simple normal distribution. So then the image in the book is up here. And I'll show an example I've worked through as well. So what I did is I set up this in Python. So can you see the text okay, or should I make it bigger?
Yeah, it's fine.
It's fine. Okay. What I've got, I've just a simple function to make a summed uniform sample. So it basically takes sum and count. So if that's 3, it'll do the uniform 3 times and sum them all up. So that's packaged up like that. And then I've made another function that repeats that, like the amount of times I want to sample, and does a bit of a plot. So now I can play with it. I've got a pretty large sample size, which is interesting, even though we're using the uniform. I've got like 10 to the 5 sample size to make sure that the histogram actually looks uniform. Then if you do 10 to the 5 samples of like 2 uniform samples summed, you suddenly switch from this flat one to the triangle one, which is pretty interesting. And the explanation for this is to do with, if you sample twice from the uniform, it's very unlikely, like if you want to get this furthest right point, you need to sample 1 twice. And that's very unlikely, but you're more likely to sample somewhere in the middle, like near 0.5 twice, or something that sort of compensates and brings you back to the middle. And then you can do it 3 times. You start getting the bell. I put it up to 10 times, you get more of a bell as it's converging towards the Gaussian. I tried playing around a little bit. I said, although I never have in real life uniform data really I can think of, but I do have like 365 data points sometimes, like for a year's data. So I was just playing around. If I do uniform with a year's data, it doesn't really look very uniform in a histogram. And I tried playing around again with, so sometimes you might have a year's data for 24 hours. So I'm just summing 24 uniforms. And I've set my sample size to 365. So just playing around with the same thing. And you can just see that, I suppose even with a uniform, if you've got like maybe a realistic sample size for your data, it's not very pretty to to try and see what distribution it's coming from. So I'll share a link to this code afterwards. And I guess there's further examples which are not uniform. So you could do something like this with the other distributions, like exponential or a power law distribution. And that's what's in the book, which we'll go back to here. So next up is the exponential. So this one, it's somewhat in between, say, a normal distribution on one hand and a power law on the other end. It's slower than the uniform, but it does relatively okay. So for 10 summands, you're getting your bell shape, but it's having trouble to converge because it's skewed. So you see that the tails are not the same on both sides. And while you might get there eventually with the exponential, it's harder as we go down with other distributions. So that would be the PDF for the exponential with one summand. Then if you want n summands, it's worked out here. So your PDF, if you're sampling n exponentials, which maps to this purple one up here. And also worked out is just the whole central limit of, if you work through here and you put n to infinity, you get this expression, which looks like a Gaussian, when you just take into account how the mean and variance are with the constants. And next we have the Pareto, which is slower again to converge. So this is up here in blue. It looks a little bit like the exponential, but it takes longer to converge, essentially. Eyeballing it. And here's a histogram with the Pareto. So in this case, if the probability density looks like this and you convert it to CDF, I think that gives you a tail exponent of 2, which is borderline for the variance stops existing if the exponent is less than 2. And that's part of why it takes very long to converge. And you see the examples here. There's a lot of data points. I tried running it and my computer went very slow for a lot of data points. So you can try and do things like Monte Carlo to handle if you want to approximate it. What else we're saying here is, again, we're looking at how it converges eventually if you really go into the limit. So there's some workings there, and then it shows how it converges to a stable distribution. So if you, with the example above, the tail is 2, so it will lead to a Gaussian. Or if your tail is less than 2, a tail exponent, it will lead to a stable distribution in the real infinity. And then next we have this half cubic Pareto, which is tail exponent less than 2, so no variance defined. It's mentioned a bit earlier in the book also. So yeah, so we're saying, like, here's an example with 1,000 data points or 10,000 data points. It's not symmetric and it won't really get there for anything realistic. So that's a run through some, starting from a well-behaved to a sort of never converging in real life distribution. And next we have looking at cumulants and convergence. So yeah, this part is a bit about the moments and how you can compare what the moments are to what they would be if you're working with a Gaussian. So for example, a Gaussian has skewness of 0, kurtosis of 3. If you're seeing moments far above that for a given distribution, then it's not Gaussian, it's fatter tailed, or it's skewed. And there's a definition here. So I'm not too good on characteristic functions, but my interpretation is on the top, you've got the deriving this, so you've got the characteristic function for n summands, and you're looking at comparing the pth moment. So if p was 4, it would be kurtosis, to the second moment. So if p is 2, it's like variance. And if that, depending on that rate, what that ratio is, how far it is away from the Gaussian, you can make conclusions. And we'll see a table further down where this expression is in the table with some numbers. Then again, staying with the idea of comparing to the Gaussian, so these blue horizontal lines are all kurtosis of 3. And then I'll make this bigger. Then just for different assets, if you take data and calculate kurtosis, it's above 3 quite definitively. And I think there's also a trend where if you've got, so this lag n, so if you go somewhere around here, you're looking at monthly. So this would be kurtosis of the monthly data, whatever it is, or maybe 10 or something is kurtosis of every 2 weeks, and you calculate it. And that's how the kurtosis is for different lags or such. And especially with the low lags, it can be quite high. Yeah, so sort of summarizing what this function k of n describes, it's basically the excess of the pth moment over that of a Gaussian. So excess of the skew or excess of the kurtosis or such over the Gaussian. And in the limit, when your moment is higher than 2, this would be 0. So if you've got, let's see, yeah, if you've go back. Yeah, we're talking about summands. So in the limit, with a really large number of summands, your skew and your kurtosis should go to 0 if it's well-behaved thin-tailed class, or it should go to finite. Whereas if it's a power law class, this term won't go to 0, and we see it below in the table to come up. And there's a few comments here about the detail of the rate at which you should expect the k term to decay, depending on what you're working with. And a comment about stochastic volatility, I think, where again things don't decay as quickly as you would expect if everything was well behaved. So okay, here's a table of this k metric and Poisson exponential gamma. Then symmetric two-state vol. As I understand it, if you plug in just your sigmas as the same, so it's just a one-state vol, then this all goes to 0, and this column would be like a Gaussian. So what you've got is, for the second moment, by definition of your k, you're doing the ratio of the second moment to itself, so everything is going to be 1. But then afterwards, when things should be 0, or whatever your reference is, like this term, instead the skew, say, of the Poisson exponential gamma is non-zero, and the kurtosis is also non-zero and not reflecting, say, a two-state vol distribution. So on to the next part. This part describes some derivations of the central limit theorem, and I'll just gloss over the high level of how they work. So starting with the Lindbergh-Levy, it revolves around having a defined mean and a finite variance. So you can work that through. So the x term is your the average of your summands, and the distribution will converge to normal when you do the appropriate adjustments. So then going further down, let's skip down to here. So the next one, Lyapunov's derivation. So this relaxes things a little bit. So you don't need to be identically distributed if you behave appropriately in other ways. So in this case, it's to do with the rate of growth of the moments has to behave according to these conditions. So this S term is like a sum of variances. So you might be summing non-identical distributions, but like the sigma I will represent the different distributions you're summing from. And then this term is the sum of those sigmas of the different varieties you're summing from. So there's some conditions that have to hold. And then finally, there's, I think the next one is slightly looser again. It's a bit similar, but it's just looser as I understand it, because the Lyapunov's condition implies that the Lindbergh's condition holds. And yeah, Lindbergh looks a bit different. There's an indicator function here, which relaxes things somehow. I'll move on to the next bit now. Law of large numbers for higher moments. Okay, so this is a fairly practical part. If you're looking at things and you want to see the fat-tailedness, you can check a few things. So you can check what happens if you add observations. Basically, it shouldn't jump around a whole lot if you add new observations. And in fact, adding more observations should reduce the variability. Then the other thing to look for would be jumps. So basically, you get your data and then you add jumps, or you look for jumps as you add up observations. And if you see lots of jumps, then you've probably got a problem with fat-tailedness. Other thing to look at would be take your data and look at subsamples of it. And if you're getting different averages, then that's probably a reason for concern. So this is maybe better explained with the pictures down below. Or first comes the table. So on top of maybe looking for jumps, look at subsamples, look at adding observations and see how your statistic moves around. You can look at how the contribution of the maximum value in your sample. So say calculate whatever you're doing and then calculate it again with the maximum value removed and see how that changes things. For example, there's this maximum to sum plot where you sum up things and you compare the size of the biggest sample in the sum versus the total size of the sum. So here we have a table. There's a lot of different assets, and you've got kurtosis. So 1 day, 10 day, 66-day kurtosis. And things to look out for here would be, well, we're talking decades here, and the kurtosis is well above 3 in all cases. Sometimes it's very, very high. Then the max quartic, I wasn't sure what this is, but my interpretation is it's to do with the contribution of the maximum to the fourth moment. So I think if you take the largest value out or put it in, the difference there is expressed as a percentage. So for example, with SP500, for the sample chosen, if you take the largest sample, it contributes 80% to the kurtosis, if I've understood it correctly. And that continues. And here we have the max to sum plot.
Yeah, just incorrect.
Okay, that's great. Thanks, Nassim. So max to sum, this is SP500 again. So given that max quartic, if that's what it is, we're looking at max and sum. So here we're starting about 60 years ago with SP500, calculating the red one is the kurtosis, the other ones are the third, second, and first moment, you mean. What happened is one of the largest movements, I guess this is 20 years ago. Not sure if it's 2008 or 10 years before that. There was a big jump because of one data point suddenly skewed everything. And here you've got, if you include or remove the largest data point, it's contributing more than 80% to your kurtosis value. So it's hard to say that the kurtosis is meaningful, because you could also think that maybe there's another massive value that would do the same and it's just missing from your sample. And for benchmarking, the one below is the normal distribution. So if you just sample a normal and run it, you won't see much happening. There's a little bit of a jump in the beginning, but even that dies out, which, as we said, we have to look for. If add more samples in something that's normal or well behaved, it will dampen out if it's not a power law, something like that. And we're getting through this pretty quickly, so if anyone wants to interrupt with questions, maybe we could briefly stop for a moment, then I'll continue. I can only see the screen.
I just have one question there, Fergal. Those that data table you had there, it looks like by the time it gets to 66 days, the kurtosis is kind of close to 3, is it, for most of them, or some of them? Oh, maybe that's wrong.
66. There are some that get here, and I think it seems clear that it's lower for the 66 day.
So it's not too far off normal for a lot of them from 66 days for like 3 months.
I guess so, although I would presume they're not normal.
Yeah, I would make a comment, the following comment: don't trust the number. You will see the ones that have a low number are the ones that have a low number of years.
Okay.
So all you have to do is wait a little bit, it jumps back up. So the way it goes is as you're adding kurtosis, you see, or you have a summation. This is summation, it blocks the 66 days. You don't have a large sample anyway, you see. As you're adding, kurtosis drops. But then over time, you have a shot, the thing jumps back up.
Okay, so I guess that's referring to this plot here.
No, it's a different representation.
Okay.
You notice, he's right, a lot of them are close to, as we see, some of them are below 3, like Swiss franc. If you add up, first of all, we have a much smaller sample. We're taking 66 days, that's how many, that's 3 months.
Oh yeah.
So you have 4 per year, 38 years. So all you need is 1 quarter, 1 more quarter jumps back up.
Yeah.
So the graph he did, Fergal was pointing at below is, I think, for 1 day.
Yeah.
See, you go for 10,000 days and then jumps back up. So
yeah.
The other one, you need a larger number of quarters. But you observe the same as quarters, we just don't have enough sample because 50 years is what? 50 times 4, 200 data points.
Yeah. Less than a year if you had it daily.
Yeah, well, a year is 250 data points. So this is so what you notice is that you don't see necessarily conversions to Gaussian by increasing your aggregation period. So large numbers, not large numbers, sorry, central limit doesn't seem to apply in practice. Okay. And another comparison, if you do a Gaussian, you'll see very quickly, whatever you have, a thin tail becomes a Gaussian, will have a kurtosis 3 rather quickly.
Yeah.
It's 20 points, you see the big gain.
Anything else? I'll finish the last part and we can get to questions. If people
sorry,
have
I'm prepared for this. I did look at the graphs. I haven't looked at these since 2008 when they were made, so I'm rather unprepared.
Okay, I'll get this last bit, and then if people think of questions as well, that's good. Basically, this is deriving the mean deviation for stable distributions. I guess this is useful because it's hard to find, say, online, the mean deviation derived.
Yeah, that was what it was derived.
Yeah. So this is a bit over my head, but if you know what, so L Heaviside function is the step function. It's working with characteristic functions and doing a convolution to combine the summands. And then it works its way through using the Hilbert transform. And it gets you out the other side with the expression, which would be the mean deviation. And there's other parts in the book which have mean deviation for other things as well, in the mean deviation chapter. So this comes out, and then it's for the stable distribution. So you have your terms for variance and skew and tail exponent. And coming up, hopefully in the next session, there's the chapter about translating between distributions, because whereas we looked at kurtosis this time, it doesn't really describe, you could have the same kurtosis in two distributions, and that sort of thing can be dealt with in the next chapter. So I'll leave it there, and we can do any questions or discussion.
And also centrally, you have distributions that don't have a kurtosis. You see, the student T that represent financial markets with 3 degrees of freedom or 2.5 degrees of freedom does not have a kurtosis. So how can you rank them if you don't? They all don't have kurtosis.
Okay.
I guess if you guys invite me again, I'll be better prepared next time on the reviews and notes.
Nassim, you have a standing invitation. Any time we talk about this, we'd love to have you here.
For sure.
Okay, so
ignore this trick. I mean, I would say that deriving the mean deviation of the stable distribution was a nice mathematical exercise with proof, but ignore. I mean, it's not something substantial or important for understanding what's going on. I just did it for pleasure, I would say, more than for to probe a complex problem. But what is important about mean deviation is that it allows you to work with, it's much more stable than the standard deviation, and it allows you to compare distributions that do not have standard deviation with one another. That's what's important about mean deviation. If you don't have the law of large numbers, you don't have statistics. So let's not talk about anything. We talk about baseball. If you have the law of large numbers, okay, then you must have a mean deviation. And then we can compare mean deviation. That's sort of like what will come up next in the next, I think, chapter.
Yeah, maybe what as an exercise, what someone in the audience can do is maybe just look at what drops out of equation 7.9 for a Gaussian versus a Cauchy, and we can then tweak some of the parameters to get close to an infinite variance and see what happens. Because if this still exists, we should see something that's reasonable to evaluate. Even if we are pushing towards infinite variance. So I think that might be an interesting exercise for someone to do. Yeah,
exactly. You should see. I expect if you do if you put an alpha, this one is alpha of 2 here is not alpha of 2 elsewhere. Okay, this is sort of like a different. When I talk about alpha, I have alpha s index s. It means alpha for the stable. Okay, alpha for the stable, because what alpha is higher than 2 for the Pareto or the student T, okay, asymptotically becomes, because they're not stable, becomes an alpha of 2 here. And alpha that are below 2 stay the same.
Got it.
You see, so any alpha higher than 2 for a Pareto distribution will become an alpha S of 2. So it's very simple. Replace 2 by alpha S. If I did this right, and I don't know because I'm very insecure as an individual, so I can't really. So I don't know if I did it right. You should have E of X should be square root of 2 over pi sigma, 2 over pi or pi over 2. The sigma is square root of pi over 2. Mean deviation is square root of 2 over pi sigma.
Got it.
So if I did things right, which we have already see here, sigma S, you can see it that the gamma of 2, gamma of 1 over, or gamma half. So should and then beta of 0, of course, because the Gaussian beta is symmetric. The Gaussian should have a beta of 0.
Yeah. Yeah, got it. That does seem to fall out. I think, yeah, so I think that would be a good suggested exercise. And if I get a little bit of time to do it, I'll definitely try it out. Maybe the way we can conclude the session is any further questions for Fergal or any of the other presenters or Nassim on the material we've covered tonight.
The only comment I make is that all the complication here comes from the beta, the symmetry. That's what messes things up. So if you have a beta of 0, then it becomes the first equation should be square root sigma times square root of 2 over pi. Sorry.
Got it.
I was
Got it. I must admit, I think I can deal with 7.9, but I was very happy that a different presenter had to deal with the derivation, and I think that was a job well done, Fergal. So yeah. So
one comment I'd like to make. Some articles here are scientific papers, and some articles are pedagogical. This one was supposed to be pedagogical. It's not scientific paper. It's like, let's say, background information, preparing for the next one, which is scientific paper.
Awesome.
So the ones that are scientific papers have been checked by referees. The best thing is to have someone who hates you. They'll find a mistake. But the ones that are not submitted to referees, they say.
That's a great way of looking at reviewer number 2, I guess. It increases the robustness of the results.
Exactly. The ones that are not scientific papers, I'm not sure about the results. So I'm very insecure, as I'm telling you.
Got it. Okay, so let's have a look towards the future. So in about a month, we're going to book the 4th session. We'll cover chapters 8 to 9, chapter 8 on how much data do you need, and this is an operational metric for fat-tailedness. I'm very excited to see that one, and then starting on the hidden tails, which I believe is where we start looking at the shadow mean. A call for volunteers. If anyone would like to present chapter 8 or chapter 9 for about an hour, or produce some code backing the monthly presentation, please get in touch with any of me, James, or Fergal, and we'll be delighted to have you present. And with that, thank you very much to my co-host. Just another acknowledgement to NOCA, which is James's organization, for kindly providing us with Zoom. Thank you very much to Nassim for joining us and enhancing the presentation, and to the wonderful audience. So thank you very much, everyone. Keep safe and well, and see you next month.
Thanks a lot. Thanks. Have a great day, everyone.